Understanding loads. In this class, we'll be studying the different type of loads. We will have some definitions, and we will look how loads are divided in different types, from dead loads, life loads, wind loads, seismic loads, etc. The type of loads acting in a structure in a building can be classified in different ways. First, if we have, for example, a column and we apply a load in the superior part of this material, we'll be speaking about a vertical load. This load can be distributed along the material and will be producing like a longitudinal load. That will happen also, for example, if we have an element like this one, like a bar that is supported and is part of another structure. We can assume that this column will be producing this kind of longitudinal loads in this material that could be in tension or in compression. In this case, it's in compression, but could be in tension if the forces are in this way. Also, when we have a material, for example, like a wall, we can have a load that add on it, like the wind, that will be an horizontal load. Well, all these loads will be acting in buildings, and they will be represented as uniform or varying force or points. Loads can be divided in many ways, and that depends of the material that you are looking for. Well, in different books, the loads will have a different division. It will not be like we are looking here, but for effects of this class, this is the classification that we'll be using. Loads will be divided in statics and dynamics. Dynamics are the ones that move and change with the time. The statics are the ones that are mostly exact, that are constant and do not move. According with the building loads, building codes, the loads will be divided in dead loads and life loads. Well, loads are divided in statics and dynamic, but the building codes work with dead loads and life loads. Dead loads is everything that is fixed in a structure, and life, everything that moves. We have also loads that are due to self-mass and thermal effects. The dead loads are the self-weight of the structure and any elements that is fixed. The life loads are related with the occupancy, people, furniture. Dynamics loads can be continuous, like earthquakes, for example, or winds, and impact, like for example, an object and car that impact in a structure. Finally, we have some environmental loads like snow that in some way is dynamic because it's natural, but also is static because change of dimension little by little, not so fast like an earthquake or an impact load. Dead loads are known as a permanent or static loads, are those that remain relative constant over the time, and are related, for example, with the weight of the building, the structural elements, the beams, the walls, the roof, any material that is fixed in the building. It includes permanent, non-structural partition, things that you cannot move in a building. Even something like a built-in cupboard. Dead loads are structures, beams, columns, walls, anything that is fixed. Well, as dead loads are all these constant loads that we have in a structure, or in a machine, the life load will be the contrary, the ones that are subject in addition to the own weight of the material. For example, people and furniture. Some loads are a little bit complicated to categorize. For example, an air conditioning system, for example, if it is applied before the ceiling finish, is a dead load. If it is applied after the ceiling finishes are complete, then it's considered a life load. Well, dead load are calculated in a different way to life load. And it's very important to understand how to calculate. Please do not get confused. This is a typical question of the test always, and many students answer this wrong. Dead load is calculated with the volume of members per unit of weight of material. What that means, you will take every material that is structural or not, that is fixed in the building, look the area or particular volume, multiply by the weight, and you will have the weight of every element of the building. And the weight of these elements will be the dead load. It's very accurate because we know the exact dimensions of the materials. And if we have, for example, a wall made out of a specific dry wall of a specific dimension, we know how much, with tables, you know how much is the weight of this material for volume. Is enough to calculate the volume multiplied by the weight, and we have material number one. And after, we will do the same with every material and every element that is fixed. Life loads, for the contrary, are code specified. What that means, they are a result of testing, there are no exacts, are subjective, and are very conservative. What we do is that we will have a building, and the codes will tell us, depending the use of the building, what is the life load that that building is supposed to have. Residential buildings, 40 pounds per square feet, for example. Industrial buildings with big machines inside, maybe 120 pounds per square feet, etc., etc. Well, one is calculate with the volume and weight of the material. The other is depending of the codes and the use of the material. Not only the codes, the use of the structure, sorry, the particular building. Well, that loads everything that is fixed. Roof, walls, floor, equipment that is fixed that do not move, life load, snow, people, furniture, any equipment that is not fixed that we can move. After, we have wind loads, that are the loads in pounds per square foot, placed on the exterior of a structure by the wind. It will depend of the angle of the wind, it will depend of the shape of the structure, and it's very important to prevent wind damage because we need to make the building stronger in order to eliminate the possibility that the building come apart. Well, the walls, the roof, the foundation must be strong, and the attachment between them must be strong and secure, especially in places where we have a lot of wind loads, like Florida. The wind will exert three types of forces on a structure. Uplift loads, that is that you will have, for example, a roof, and the roof will tend, for example, with the wind, to move up and deform, like in this way. Also, we can have a shear load. We have a wall, and when we apply a wind in this wall, the wall will tend to move and to break into parts or more parts. And finally, we have a lateral load, that is the one that if we have, for example, a wall and we apply wind, the wall will tend, or the structure will tend to move and displace to a different position. When we have a building, in one side we will have the pressure of this wind that will act in the structure, but after, the effect of this wind will tend to create in the other side of the building suction. Well, the pressure will create suction, and that is very dangerous and can break a building. We need to understand that if we have a load, like for example, let me go back, like for example, this particular small load of a wind that is applied in this point, the load maybe is not so big, but imagine all these loads together in a very tall building. And imagine, for example, the effect of this L load that is a force W that is multiplied by all this distance. It will create a moment here that will tend to overturn the building in this dimension. Therefore, this small wall multiplied by this tall distance will create a very big reaction. If not, the building will move or tilt. Well, wind loads are very important in tall buildings. Finally, we have seismic loads. It's basic in earthquake engineering, and it's like an oscillation. The floor will move, it could move up, down, could move left and right, that is a lateral load, and will create a lot of movement that will make the material to break. When we have a seismic load, what will happen is that the wall will be like dynamic, and we will have some vibration in the structure. And dead loads, live loads, no loads usually act very slow in the material, but the earthquake instead is a very strong and rapid movement and will cause big problems. What happens with an earthquake is that the material will move very fast to the right and very fast to the left, and in that process can break. A part of that, we have the gravity loads that are the weight of material. We have elements such as wind can be the top of the material. We have lateral loads, and all these forces will tend to create some kind of destabilization in the building. And the idea is that the building needs to be designed in a way that is stable. Well, about occupancy loads, that depends of the type of material. For example, if we have the type of building, sorry, if we have a residential material, the occupancy load will be as small as 40 pounds per square feet. But when the material have like heavy manufacturing elements there, or for example, when we have armoires, there is a lot of elements inside, and the material will be supporting a lot of weight. Therefore, the loads are much bigger. Like for example, for armoire is 150 pounds per square foot. Those loads are in the building codes. Well, there are other loads like lateral loads, for example, due to pressure, air pressure, and many others that we need to consider when we are speaking about buildings. Buildings need to be designed to resist these loads. And one very interesting fact is this building called Taipei 101 that is located in Asia, in Taiwan. It was the tallest building of the country, and is located in a place where they have a lot of earthquakes. And well, how to make a building in a place that we can manage that? Well, what they decided to do with this building is that in the superior space part of this building, there is a big space with an element that is like a metal ball, very big and very heavy. Look the human scale. I had the opportunity to visit this building, and it's open for the people to look what's going on. Well, we have this huge ball, very heavy, that is hanging from the building. And when there is an earthquake or even strong winds, the ball will move to the contrary side. Will be like a counterweight. If the building moves to the left, then the ball will move to the right. And that will allow the building to stay in place, because will act contrary to the forces that the building is suffering. As a homework, please read the chapter 1 of the textbook, and this concludes this presentation.